So my question is that an object of mass m moving along the x-axis with velocity v is slowed by a force F equals negative kv, where k is a constant. At time t equals 0, the object has velocity v at position x equals 0, as shown above. So I represented that by my diagram right here, and I made the left negative and the right positive. So we know that the resistance force is force equals negative kv, and we know that force equals ma, so we can set ma equal to negative kv. We then isolate a, and we have a equals negative kv over m. So we know that the magnitude is kv over m, and the direction is left. So that's part A. I'll just write acceleration equals negative kv for m right here, because we're going to need that for part B. Part B says, derive an equation for the object's velocity as a function of time and sketch this function on the axis below. Let a velocity directed to the right be considered positive, which we had already done. So now I have to derive an equation for the object's velocity. We know that acceleration equals dv over dt, so we can set that equal to negative kv over m. I then have to separate the variables and move the velocity from this side to the left and dt to the right, so I'm left with negative k over m dt. Now what I have to do is integrate. So I see that v to the negative, v is on the bottom, so it becomes v to the negative 1. V to the negative 1 is ln of v, and that equals negative k over m t, because I just get rid of the d. I'm integrating dt. I know that velocity goes from VO to V, and time goes from 0 to t. So now I have to find out my initial, so I know ln v minus ln VO equals negative k over m t, and then minus negative k over m times 0, which is just 0. Then I know the property of ln v minus ln of VO is just ln of v over VO, and that equals negative k over m to the t. I'm just going to erase this for more room. So now to get rid of the ln on this side, I have to take the natural log of both sides, raise this to the e, and then ln and e cross out, and I'm left with v over VO. Do the same on the other side, e to the negative k over m t. Then I have to get velocity by itself, so I multiply by VO, and I'm left with velocity equals VO e to the negative k over m t. And that is my formula for velocity, and I have to graph this as well. So with velocity as a function of time. So I know that when velocity is 0, when time is 0, I set time equal to 0. So it's e to the 0, which is just 1. So v equals VO. So initial velocity is equal to v. Then as time approaches infinity, I know that this just becomes e to the negative infinity, because infinity divided by whatever number is still infinity. So e to the negative infinity just becomes, it's basically 0, so v equals 0. But e to the negative infinity never really equals 0, it just gets so little it's almost 0, so the graph approaches 0 as time approaches infinity, but never hits 0. So it looks like that. So that is part B. That is the final equation for velocity. Velocity equals VO e to the negative k over m t. We need that for part C now. Part C asks, derive an equation for the distance the object travels as a function of time t, and sketch this function on the axis below. So we basically have to do the same thing I just did for velocity for position. So we know velocity equals dx dt. So dx dt equals VO e to the negative k over m t. Now we have to integrate, so we have to move dt over to the other side, and we have dx equals VO e to the negative k over mt dt. So now we know position goes from 0 to position final, and t goes from 0 to t final. Now we have to further integrate, and we have 0, so it's just 0, and x, which equals VO e to the negative k over mt, and dt equals, when we integrate that, negative m over k. Now we have to subtract from when time equals 0 here, and when time equals 0, this is just 1, so we're left with VO and then dt, which is negative m over k. Negative VO m over k. So this is, so now we see that they both have in common VO and m over k. So we're going to pull out, sorry, I'm just going to erase more. Sorry, room. We're going to pull out a VO m over k. So we have x equals VO m over k, and then what we're left is here is negative e to the negative k over mt plus 1. And that is our final equation for position. Now I have to graph position as a function of time. And if I plug in 0 for time here, I see that position also equals 0 because I have 0 for time here, which ends up just giving us negative 1, and then negative 1 plus 1 is 0, so 0 times this is just 0, so time starts at 0. Here's x. Now as time approaches infinity, we can see if we plug e to the infinity, we really just have negative e to the negative infinity, which just equals 1 minus 1 minus 1 over e to the infinity. And that equals 1 minus 0 because we have a bounded number over a large number, so that equals 1 minus 0. So this in here all becomes 1, so we're left with VO m over k, which is just x. So we see as time approaches infinity, position approaches VO m over k. Part D, remember, VO m over k times 1 plus e to the negative k over mt. That's the final equation we're left with. We have x equals to that. Now part D asks, determine the distance the object travels from t equals 0 to t equals infinity. We did that basically when graphing in part C. So when time equaled 0, position was 0. And then as time approached infinity, we saw that this all wiped away to just 1, so position ended up just equaling VO m over k. And that's the end of my question.